The work formula from last video, F dot delta R, carries two hidden assumptions. The force stays constant and the body moves in a straight line. Real motion breaks both. A planet swings around the sun on a curve while gravity changes direction at every point along it. A spring pulls harder the farther you stretch it. This video removes both assumptions with one tool, the line integral. Chop any curved path into tiny displacement vectors, dot each one with the force acting right there, and add the pieces. Any force, any path, one definition of work. Set the stage. A force that varies from point to point acts on a body of mass m, while the body moves along a curved path in 3 dimensions. Measured from a chosen origin, the body's position at time t is the position vector r of t. The body starts at the initial position, r sub I, and ends at the final position, r sub f. Now divide the travel time into n small intervals. During interval number j, the body moves from position r sub j minus 1 to position r sub j, and the displacement for that interval is the vector delta r sub j. The difference of those two position vectors, a short chord pointing along the path. The force may change during the interval, so use its average values there, F sub j average. The work done during interval j is their scalar product. Delta W sub j equals F sub j average dot delta R sub j. Now add every interval. The total after n pieces, W sub n, is the sum from j equals 1 to n of these scalar contributions, one number per piece, summed into one number for the whole path. The sum W sub n still depends on how we chop the path. A coarse chop with long chords cuts corners, so take the limit. Let n go to infinity while the length of every delta R sub j shrinks to 0. The chords hug the curve ever more closely, and the distinction between the average force and the actual force at each point disappears. If this limit exists and is well defined, it is the work done by the force. W equals the integral from I to f of f dot dr. This limit is called the line integral of the force, and the symbol dr is the infinitesimal vector line element, the limit of the displacement vector as the time step goes to 0. At every point, dr lies tangent to the orbit. Notice that the time parameter has dropped out entirely. Only the geometry of the path remains. And notice what kind of object we built. Every piece was a scalar product, so the sum adds plain numbers. Work is a scalar, not a vector. Look at what the definition actually says. The integral runs from the initial point to the final point, but it is evaluated along a particular path, and in general, the path matters. When the force varies from place to place, the products f dot dr sampled along one route differ from those sampled along another, so two paths joining the same endpoints can accumulate different amounts of work. Do not assume work depends only on where you start and where you finish. For a general force, it also depends on how you travel between them. Some special forces will turn out to give the same answer for every path. That exception is so important it earns its own name, the conservative force, in the chapters ahead. The honest general statement is the one to remember. The value of a line integral depends on the path taken. To compute a line integral, you choose coordinates, and the first job is writing the line element. In Cartesian coordinates, an infinitesimal step splits along the axis. dr equals dx I hat plus dy j hat plus dz k hat. 3 tiny displacements, one per axis, adding up to the step along the path. Write the force in components as well. F equals F sub x I hat plus F sub y j hat plus F sub z k hat. Now dot the two expansions. Matching unit vectors multiply to 1, and mixed pairs multiply to 0. The orthonormal rules from the scalar product video. So 9 possible terms collapse to 3. dw equals f sub x dx plus f sub y dy plus f sub z dz. Each component of the force does work only along its own direction. Integrating from the initial position to the final position, the one-line integral splits into three separate integrals, each still taken along the path. The integral of f sub x dx plus the integral of f sub y dy plus the integral of f sub z dc. Some forces ignore Cartesian axis. A pull toward a central point or a push that circulates around an axis singles out radial and angular directions, cylindrical territory. Locate the body by its distance r from the axis, its angle theta, and its height z. The line element now has three pieces: a radial step, dr along r hat, an arc step, r d theta along theta hat, and a vertical step, dz along k hat. Watch the middle piece. A change of angle is not by itself a length. Sweeping through the small angle d-theta at radius r covers an arc of length r times d-theta. That factor of r is the one genuinely new feature. Write the force in the same basis F sub r hat plus F sub theta, theta hat plus F sub z k hat and dot the expansions. These unit vectors are also mutually perpendicular, so the same collapse happens. dw equals F sub r dr plus F sub theta r d theta plus F sub z dz. And the total work is again a sum of three integrals along the path, one per component. Two coordinate systems, two expansions of the same definition. The skill is choosing between them. Match the coordinates to the symmetry of the force. Uniform gravity points along one fixed direction, so choose Cartesian axis with one axis along the force. Then two of the three force components are zero and two of the three integrals vanish before any computing starts. A central force pulls along the radial direction, so choose cylindrical coordinates. Only the radial component survives and the line integral shrinks to a single term. That collapse is the whole strategy of the two examples coming next. Pick coordinates well, and the three-term line integral becomes one ordinary integral. First worked example, uniform gravity along a curved flight. A body moves under gravity alone along a parabolic path, a projectile arc. The force is constant, F equals minus mg, j hat, the same magnitude and the same downward direction at every point. The body starts at the point x sub 0, y sub 0, and ends at the point x sub f, y sub f. Find the work done by gravity along this flight, set up the line integral. The motion stays in a vertical plane, so the line element needs only two terms, dr equals dx I hat plus dy j hat. Form the scalar product with the force, F dot dr equals minus mg, j hat dotted into dx I hat plus dy j hat. Distribute the dot product. J hat dot I hat is 0, so the horizontal term dies completely. J hat dot j hat is 1. What remains is F dot dr equals minus mg dy. Read that physically. The force is purely vertical, so horizontal progress contributes nothing to the work, no matter how far the parabola ranges sideways. The line integral now collapses to one ordinary integral over height. W equals the integral from y sub 0 to y sub f of minus mg dy. The integrand is a constant, so the answer is immediate. W equals minus mg times the quantity y sub f minus y sub 0. Interpret the result. The parabola has vanished. No trace of the path shape survives. Only the starting height and the ending height. Any other route between those same two endpoints, straight, wiggly, or looping, gets exactly the same work from gravity. For this constant force, the work integral is independent of the path, and the sign carries the physics. If the body ends below its start, y sub f minus y sub 0 is negative, the two minus signs cancel and the gravity's work is positive. The force pointed along the descent. If the body climbs, gravity's work is negative. The force opposes the motion the whole way up. Second worked example, and this time the force genuinely varies with position. A spring rests on a frictionless horizontal surface. One end is fixed to a wall, the other end attaches to a body of mass m. Find the work done by the spring force as the body moves from an initial position to a final position. The coordinate choice does the heavy lifting, so set it up carefully. Place the origin at the center of the body when the spring is relaxed, the equilibrium position, and let x be the body's displacement from that origin, with the positive I-hat direction pointing the way the body moves as the spring stretches. Hooke's law then gives the spring force. F equals F sub s I-hat equals minus kx I-hat. Check the signs. Stretch the spring. X is positive, so the force is negative. It pulls the body back toward the wall. Compress the spring. X is negative, so the force is positive. It pushes the body away from the wall. Either way, the force aims at equilibrium, and its strength grows with the displacement. A constant force formula has no chance here. This is precisely the situation the line integral was built for. The body moves along the x-axis, so only the x term of the work integral survives. W spring equals the integral from x sub 0 to x sub f of minus kx dx. Unlike gravity, the integrand is not a constant. X itself is the variable of integration. The antiderivative of x is 1/2 x squared, so evaluating between the limits gives W spring equals minus 1/2 k times the quantity x sub f squared minus x sub 0 squared. Interpret the result. The work depends only on the squares of the endpoint displacements. Each endpoint's distance from equilibrium, regardless of side, with no memory of the motion in between. Move the body from equilibrium outward in either direction, and the spring does negative work. The force resisted the whole way. Let the body return toward equilibrium, and the spring does positive work. And look at the form of the answer, 1/2 kx squared, evaluated at the two ends. That combination will earn a name of its own in the chapters ahead. One definition now covers every force and every path. Work is the line integral of f dot dr. Chop the path into displacement vectors, dot each one with the local force, add and take the limit. To compute it, write the line element in coordinates matched to the force, Cartesian steps or radial arc, and the vertical steps with the factor rd theta. And the integral splits into one term per component, with the right choice killing all but one. In general, the answer depends on the path taken, yet both of our examples refuse to. Gravity's work needed only the change in height, and the springs needed only the endpoint displacements. Forces like these let work be stored and recovered between positions. That idea becomes potential energy, a few steps ahead. First, we turn this line integral loose on the inverse square force of gravity. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.